Okay, so tonight's the night, it's the last night before the AP Calculus exam. And you want to get a little bit of last minute review in. That's why I'm making this video. Okay? So I've got a few things that I'm going to remind you of that are things that you can control to, maximize your outcome tomorrow morning. Okay? Now the first and most obvious thing that you can control, right? You can't control if they do some sort of weird free response question or if they ask you the most difficult multiple choice question you've ever seen in your life. Can't do anything about that. One thing you can certainly control is knowing all the formulas that you are expected to know. Now, I'll just say right now that this video is for AP Calculus BC, so some of these things might not be, applicable to Calculus AB if that's the class you're in. But, all of my kids are in Cal BC, so this is going to be a list of Cal BC things to know. All right. Right, these are the things that I've told you throughout the year you are expected to have memorized, and that is just the weight you have to pull, right? I need you to know your formulas. But compared to a lot of the other stuff that I've asked from y'all this year, this is really not very hard. So one thing we need to know would be the integral of u dv. Okay, this is a BC only topic. Okay, this is u times v minus the integral of v du. Integration by parts, don't forget it. Okay? You need to know a bunch of derivative rules. Okay, and I will try to kind of list those out to the side here. Okay, derivative rules. In fact, there's so many of them, I might just kind of like make a 2-column chart off to the right. Okay, obviously we need to know our derivatives of polynomials and sine and cosine. Those are so obvious, I'm not even going to go into those. The derivative of e to the x and log of x, again, we just use those every day, so we're not going to really need to worry about that. Okay, so let's talk about derivative of tangent x. Okay, that's secant squared x. Okay, there's cotangent x. And if you know the derivative for tangent, what you're going to do is you're going to make it the cofunction, so it's cosecant squared x, and then you're going to make it negative. Okay. Secant. And of course, we could do this by, using the quotient rule, calling this 1 over cosine, and then using the quotient rule, but that's very, very time consuming, and you might not have that much time tomorrow. Who knows what's going to happen? Okay, make it the cofunction, and make it negative. Okay. What else do we need to know? We need to know our arc-trig derivatives. Okay, I need to know the derivative of arc sine. Okay, that's the positive one. Arc cosine is the same as arc sine, just negative. Arc tangent is the easy one. That's 1 over 1 plus x squared. And that is a derivative rule that I feel like, I don't know, just might show up as an antiderivative question. There might be some sort of like complete the square type thing in the denominator. And I'll have more information on this in just a little bit. What else do we need to know? Okay, we need to know, the derivative of f inverse. Okay, and that's another thing I will do kind of in its own thing, because it's been a while since we've done that. Okay, so the derivative of f inverse is 1 over f prime of f inverse. Okay, now this can be proven using the chain rule, using the fact that, f of f inverse of x is equal to x for all x, provided a function has a well-defined inverse. But the thing I'm going to remind you about this formula, and I will remind you this again when we go to actually do an example, is that f inverse is an x value. Okay, f inverse, okay, we know that f is a function that takes in x's and gives you back y's. F inverse does the opposite. It takes in y's and gives you back x's. So it's 1 over f prime of some x value that corresponds to y equals whatever we're putting into f inverse. But I'll tell you more about that. Okay, those are kind of our derivative rules. We also need to know our Maclaurin series. there's 4 of them that we just absolutely have to know, but if for each of them I have like a little trick, right? Sine of x is an odd function. I'm just going to write this in the memory trick, and then I'll write the series below. Sine of x is an odd function. And since it's an odd function, its Maclaurin series has only odd terms. So that's x to the 1 minus x to the 3 on 3 factorial plus x to the 5 on 5 factorial, and so on. Okay, we know that cosine x is an even function. So its terms, it'll start with the 0th power, that's 1 minus 2 power, 2 factorial, 4th power, 4 factorial, and so on. Okay, e to the x, I'm proud of this one, I thought of this one myself. It's easy. It's x to the n over n factorial. So that's 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial, and so on. All the way up to x to the n over n factorial. Then 1 over 1 minus x. And okay, I don't really have the best one for this one, except for kind of to tell you that it's geometric. Oops. Remember I told y'all last year in pre-cal, or you've heard that the sum of an infinite geometric series is the first term times 1 over 1 minus r. Okay, so that means that the first term is 1 and the common ratio is x. So it's 1 and each time I multiply by x. Okay. These are the Maclaurin series that we're expected to know. We're expected to know the formula for polar area. Okay, we need to know that basically when switching from f of x dx to f of theta d theta, you need to have another power of r in there for reasons that I showed you earlier in the class and that will become more obvious if you take a multivariable calculus course. The polar area formula is you have to do 1/2 r squared, and when we're integrating. So don't forget to do that. Okay, they will always have a distractor answer choice on a multiple choice setting that is twice as much as the correct answer, where you've remembered to square it, but you've forgotten to divide by 2. Don't forget to divide by 2, please. We need to know how to take the arc length of a graph or a piece of curve. Okay? Now, it depends on how your graph is given. If it's y equals f of x, that would be like rectangular. No, then it's the integral from x1 to x2 of the square root of 1 plus dy dx squared dx. But if it's, given parametrically, y equals some function of time and x is some other function of time, yeah, I guess rectangular wasn't exactly what I meant. I think I meant maybe explicit or something like that. Because rectangular is usually, as opposed to polar or some other spherical type of coordinate system. But either way, my point stands. If it's given to you parametrically, what you're going to do is you're going to integrate over some sort of time interval, and then you end up with dx dt squared plus dy dt squared dt. All right, so these are the arc length formulas. Really, the thing that gives these away is the kind of the variable of integration, right? If it's given to you as x equals some function of t and y equals some function of t, um, you don't go back to dy dx. We can find dy dx on a parametric curve, right? We take dy dt and we divide it by dx dt. That's probably another thing you need to know. There's probably a few more things on parametric equations that I would, say you need to memorize, but I'm not going to include it in know your formulas. But okay, so basically, if it's given parametrically, you need to find the length, which is the same as the total distance traveled. But if it's given to you rectangularly, you need that 1 plus dy dx squared formula. If you're curious about why that is the way that it is, then I would suggest you go back and watch my video on area and perimeter. All right, I've thought of one more. You need to know how to take the second derivative of a parametric curve. Or not really take the second derivative, but determine the concavity. Okay? And so the thing that you need to remember is that when you go to take the second derivative of y with respect to x both times, dy dx is dy dt over dx dt. It's some function of t. What you got to do is you got to take the derivative of dy dx, and then you're going to divide by dx dt afterwards. Everyone always forgets to divide by dx dt. And honestly, this is the type of thing that I always, every year, I hope it just isn't on the exam because, even some of my better students, they just forget to divide by dx dt. Okay? But don't let that be you if you're sitting there and you're studying for the exam tomorrow morning. And they ask you for the second derivative, when they give you x as some function of t and y as some function of t, do not forget to divide by dx dt, please. All right. The second thing that I just really want you to be able to do when you step into the gymnasium or wherever you're taking your AP exam tomorrow, I want you to be able to antidifferentiate and differentiate exponential and log functions where the base isn't e. Okay? I have not done a good enough job this year. I have never done a good enough job in my Cal BC classes of utilizing this example. And I would just hate for you to be caught unprepared. Okay, so first what I'm going to do is I'm going to take the derivative of 10 to the x. You're like, well, I know the derivative of e to the x, but I don't know the derivative of 10 to the x. I know it has to do with the natural log of 10. Okay, yes, you're right, it does have to do with the natural log of 10. But I can never remember, do you multiply by it or do you divide by it? I don't know. And I work with this stuff every day. So what I'm going to do is I'm going to take 10 to the x, and I'm going to rewrite it as e to the log 10. And then when I take 10 to the x, really I'm just going to multiply that in the exponent. Now I just have a chain rule problem. Okay, so this is e to the log 10 times x. And then the derivative of log 10 times x, right there, the derivative of the inside, well, that's log of 10. Right? It's just a line with slope log 10. And then I'm going to kind of rewrite this as the log of 10 times, but then e to the log 10, that's just 10 times 10 to the x. Okay, so we multiply. If you had to antidifferentiate 10 to the x with respect to x, I would tell you to do the same thing. E to the natural log of 10 times x. Okay, we know that e to the u is its own derivative, antiderivative, derivative. If it's its own, then it's the same thing. But for the chain rule, when I do take the derivative of this, I'm going to need to prepare for this to come out with the chain rule, so I need to make it like a soft landing spot. And so I've done that, and it's like, okay, that doesn't look all that familiar. Shouldn't the antiderivative 10 to the x be related to 10 to the x? And yes, it is, because e to the log 10 is just 10. So that's where we divide. Okay, I'll real quickly run through the log examples, but it's very similar. Now with the logs, I'm going to have you use the change of base formula. So I'm just going to remind you that if I wanted to take the derivative with respect to x of log base 10 of x, that's the same as taking the derivative with respect to x of the natural log of x divided by the natural log of 10. And that's going to be pretty easy because natural log of 10 is just some number. And that's going to be 1 over x, because the derivative of log is 1 over x. Okay. And then the antiderivative of log base 10 of x is even easier. Well, actually, no, it's not. The first step is easy. It relies on you knowing the antiderivative of natural log. So I find this one to be highly unlikely for AP calculus purposes. And I can guarantee that this is not eligible for calculus AB. Okay, so again, I'm going to use the same log property. Okay, and I can factor out this constant. But this antiderivative of natural log of x, okay, you have to use integration by parts. Okay. Oh, another thing you have to memorize, I-late, right? Inverse trig, least desirable to be dv, okay? When you're doing integration by parts, u and dv, okay? But I'm probably not even going to go back and do that, okay? Exponential, very desirable for dv. Very easy to anti-differentiate. That's the deal with I-late, okay? And that's pretty much what we've got for derivatives and antiderivatives of exponential and log where the base is an e. Next, we have a topic that I have always neglected in my AP Calculus classes, but I will not be neglecting in the future after a particular free response item that I saw on some kind of practice test that was put out by the College Board. I felt like they were speaking to me. They were telling me, Huff, you have not been instructing these children on the derivatives and antiderivatives of absolute value, and I will not make the same mistake again in the future. Because, man, on that practice test, that was not a highly scored on item. Okay, and the sad thing is that y'all actually know about the derivative of absolute value. You're very familiar with this function. We just look at it in a different context. Okay, I'm just going to draw you a quick little picture of y equals absolute value x, and we see there it's slope 1, and here it's slope -1. So, you know, the derivative should be 1 and -1. 1 where x is positive, and -1 where x is negative, and undefined where x equals 0. And if you think about it for a while, it's like, wait a minute, I know that function. Maybe if I drew a picture of the function, you would know what I meant. It's like, oh yes, there it is. That is absolute value x divided by x. And, okay, it's 1 where x is positive, it's -1 where x is negative, and it's 0 where x is undefined. Now, the antiderivative, you know, it's like we always talk about this in terms of like limits at the beginning of the year and stuff, but I never actually use the function, and it's like, oh, they don't really need to know it's on the exam. Who knows? Maybe it is on the exam. And man, would I feel bad if that was like a real operational free response question, and y'all weren't prepared for it. That would be terrible. Okay. Now, antiderivative of absolute value of x. I'll just tell you it's 1/2 x absolute value x, and this is just so unlikely to appear. Now, the derivative definitely could appear, but the only thing I'll tell you, I'll draw this picture again, and you see if this is x and that's x, this area would be 1/2 x squared, right? But if I were to start going backwards, now of course this all depends on, you know, an initial condition or something like that. But if I go over here and I'm just, you know, saying starting at 0, I've got x and x, it's another 1/2 x squared. But if I'm counting backwards, I'm going to be needing that to be -1/2 x squared. And this seems to work pretty well. Credit to a few different people in my Cal BC class, I believe 403, 490, you know, I can't think of who else, but I had some people solving this and bringing this to me and telling me that this was a valid antiderivative. And I do appreciate that because nobody ever told me about a valid antiderivative for absolute value of x. Probably just because I never thought to ask that question, right? I'm sure there were guys that knew it. I just didn't even know what I didn't know when I was y'all's age. All right, so that's the deal with absolute value. Okay, here I've got one that I'm not convinced has ever come up, but it's definitely legal to come up. But if it was tested, it's so easy. I'd hate for y'all to get caught off guard by it, right? There's so many of these things. It's how I feel. Okay, so I'll just, give you an example. What if you were asked for an antiderivative of, I'm just going to make one up, x to the third minus plus 5x minus 10 or something. I feel like the sign change might help. Over x plus 3, or I could just be misapplying the Descartes rule of signs. I don't know. All right, well, oh, I see, I have misapplied the Descartes rule of signs. These numbers are going to get bad. Anyway, don't worry about that. Okay, what you need to do is you say this is bigger on top. This is not a UDU type situation. So you're like, oh no, what am I doing? What do I do with this integral? How can I simplify the integrand to make it friendlier on me when I want to go anti-differentiate? You're going to long divide. Except, I suspect that for the College Board stuff, for the AP exam, it's like all about, efficiency and stuff. I highly doubt you would need to long divide. I expect synthetic division will be the trick. Now, if you're one of those people, I have had y'all in my class before, and you're like, I don't like synthetic division, I prefer long division. Be my guest. Have at it. But don't come complaining to me when you don't get all the way to number 90 on the calculator section, or you don't finish all of the things, because you wasted all of your time long dividing two polynomials just so you could anti-differentiate, right? Okay, anyway, I'm just going to set up for synthetic division. I'm going to use synthetic division for sure. 1x to the third, I had to make one with a missing term, right? Don't want you to forget about that. If there's no x squared, you put that 0 there. 5 and negative 10. Now, knowing what I know about how about the College Board items, I highly doubt they would put one that was missing a squared, because then it becomes all of a sudden it's more of an algebra question than a calculus question. But we definitely need to be able to put negative 3 in there. Right, see, these numbers are getting out of control. 14 times 3 is, well, it's 30, and 12 is 42. This is negative 52. All right. So what I'm actually doing is, okay, this quotient is 1x squared minus 3x plus 14 minus 52 divided by the divisor, x plus 3. Okay, so I'm anti-differentiating x squared, negative 3x, 14, and negative 52 over x plus 3 with respect to x. And now this is a very easy integral, right? Everybody in my calculus classes knows how to anti-differentiate this. We're going to increase the power by 1 and divide by the new power. We're going to increase the power by 1 and divide by the new power. We're going to increase the power by 1 and still divide by the new power. Well, maybe, and never a bad time to remind you of something you already know. Okay, this is 52 times x plus 3 to the negative first power. If you were to increase the power by 1 and divide by the new power, you'd be divided by 0, which is how you know you need to use a log. Okay, so minus 52 logs of the absolute value of x plus 3. And, of course, you wouldn't want to forget your plus c. Okay, that's what we do with bigger on top integrals. All right. Now, we know that the majority of bigger on bottom integrals are going to kind of come down and either be like UDU, or if they're factorable, it'll be partial fractions. It's usually pretty obvious what you're supposed to do. But every once in a while, you might come up against an integral like this. It is not factorable in the denominator, but it's close to being factorable in the denominator. Okay, the 11 is just a distraction. Okay, but the big thing is that this is just a little bit off. Okay, what I'm going to do is I'm going to just grab this denominator and I'm going to point something out. I'm going to say that x squared plus 10x plus 26, not factorable. Okay, if it was plus 15 or plus 27, I feel like it would be, or minus 15, right? Negative 13, negative 2, or minus 27. That's something that we could work with. I don't know if there are any other factors of 26 I'm not thinking of. I think not, because of the lack of ways to divide 13, but either way, if this was 25, then it's a perfect square, and that's really nice. And you just got to be on the lookout for things that are just a little bit off from a perfect square. Okay, x squared, 10x, and 25 plus 1. Because the thing is, this that I have just highlighted is a perfect square in the denominator. And that's promising. So this is x plus 5 squared plus 1. So what I'm going to do is I'm going to actually do this integral, and I'm going to integrate this from -5 to -4. And be like, why -5 and -4? But I do have a reason for this as well. Okay, so what I'm going to do, first things first, I'm going to factor out that 11. Gotta factor out that 11. Okay. And then I'm going to have 1 over, who knows? Maybe you're just sitting at home and you're like, dude, I do not see what you're going for here. 1 over 1 plus a thing squared. That's the derivative of something. That's one of the derivatives I have to know. Okay, 1 over 1 plus u squared. 1 over 1 plus u squared. Where is it? Oh, I deleted all of them. Okay, it's one of the formulas that we're expected to know. Basically, I'll just tell you. That's the derivative of arctangent. So when I antidifferentiate this, I'm going to get 11 arctangents of x plus 5. And I'm going to evaluate that from -5 to -4. Now, a discussion I was having with our Calculus AB teacher recently was exactly which values of arctangent and arcsine and arccosine are we expected to know? And what is and isn't reasonable there? Okay. I believe that I don't think you're expected to know arctangent of square root of 3. I would really prefer for you to, because it's just good pre-calculus knowledge. But I think arctangent of 1 and arctangent of 0 and maybe arctangent of -1. Oh, and also certainly the limit of arctangent as the argument goes to infinity. That's going to be one you need to know. That goes pi over 2. The limit of arctangent is pi over 2. But I think just 1 and 0 and -1 is what I'm thinking. Okay, so what I'm going to do is I'm going to say that this is 11 times arctangent of -4 plus 5 is 1 minus arctangent of 0. And yeah, I went off the window a little bit, but so the thing is, okay, arc whose tangent is 1, you think to yourself, where is tangent 1? Well, that's at pi over 4. And where is tangent 0? Well, tangent is 0 at a bunch of places, but most obviously it's 0. So this is looking like 11 pi over 4. I thought that was nice. That's something that you definitely need to know. It's explicitly mentioned in the AP Calculus course description, integration by completing the square, so I'd hate for anybody to get caught off guard by that. All right, I've only got a couple more for you, and this video is already getting a little bit longer than I had anticipated, but one that was brought up this morning in second period was average value. And somebody said, what about average value? I said, you're right. We have not done average value in a long time, and that would be a real shame for someone to get that wrong. Okay, so remember, you know, if you're in, say you're in my, I don't know, next year in my financial math course, that's going to be graded pretty simply. I think it's probably just going to be mostly classwork grades, right? You want to know what your average is. You're going to add up all your grades, and then you're going to divide it, right? Okay, that's how we're going to find an average value of a function. So f average is going to be, you're going to add it all up. So you're going to average, or you're going to add up all the values of the function, which is kind of what integrating is, in some sense. And then we're going to divide by the number of numbers. Now, we can't divide by infinity. That doesn't make sense. Division is only a operation defined, you know, between two real numbers. So we're going to divide by b minus a. And that is the average value. I don't think I even need to do an example of this. If you need more, go watch my average value video. I did lots of examples in that video. That's just something I would not want anybody to forget. Actually, you know what? I've got something. I don't know if I put this on the video when I did average value the first time, but I want to make a connection for anybody that's just made it this far, made it to 30 minutes in the video right now. let's just go ahead and look at average value of the derivative and average rate of change. What is the relationship there? Let me tell you, they're all the same. Okay, the average value of f prime, so the average value of the derivative, is the integral from a to b of f prime of x divided by b minus a. But I can take this integral up top. This is easy. Okay, this is f of x from a to b. So this is f of b minus f of a over b minus a, which is the average rate of change of the function f on the interval a to b. So that's another thing I'm going to tell you. The average rate of change is exactly the same as the average value of the derivative, in case that thought had ever crossed your mind. And if it hadn't, then no big deal. It was just 1 extra minute on this video. It's already kind of long. All right, now, let me tell you, derivatives of inverse functions. This is a thing that I also nearly forgot, but was suggested to me by 525 this morning. And 525, I'm pretty sure you know how to take the derivative of an inverse function. I think you might have just been looking out for your fellow classmates, and that's very appreciated. And maybe, who knows, maybe you did forget. I somehow doubt that, though. All right, 525, very conscientious student. So let's just write down the rule, and then I'm going to bring in a couple of questions from earlier in the course and try to, work on those. All right, remember the formula is that the derivative of, I'll say, f inverse prime is 1 over f prime of f inverse, where f inverse is an x value. All right, that is an x value. All right, so what I'm going to do is maybe I'll bring in a couple of questions from that unit test. Okay, we've found one. Here, the table is giving selected values for a differentiable and increasing function f and its derivative. Okay, the increasing thing is actually just the fine print that makes sure that the function is invertible, and you do not need to worry about that at this level of the course. If g is the inverse function of f, what is the value of g prime of 3? All right, so we know the formula, right? We know it's 1 over f prime of f inverse. Okay. So the first order of business is finding out what f inverse is. F inverse of 3 is the x coordinate that corresponds to f of x equals 3. This is looking like we're tracing back to 1. So this x value is 1. 1 over f prime of 1. And, okay, that is 1 over 4, which is answer choice B. All right, another table one. This is great. We've got another inverse function, and we want the derivative of the inverse at x equals 4. So we're going to find f inverse of 4. Okay. Again, I'm going to write down the formula. That's the best way to remember the formula, not to forget it, is by writing it down a bunch of times. It's like UDD. I made you write it down every single time. And then, some people never forget. Okay, so this is 1 over f prime of f inverse. Okay, f inverse of 4, well, that's where f of x equals 4. Now, this table actually would have given it to you. I still don't think that this is the way to go, though. Okay, f of x equals 4. Okay, we track back to x, that's negative 2. 1 over f prime of negative 2, so, is 1 over 4. again, 1/4. Okay? Tomorrow on the exam, do not just choose 1/4 because you saw all of my examples coming back 1/4. I've got one that won't come back 1/4 right here. 490, I know that's you. You would do that. Okay, here we got one more. We've got 2x plus e to the x. G is the inverse function again. What is f inverse's derivative at x equals 1? Well, first I'm going to need to find f inverse of 1. Okay, f inverse prime is 1 over f prime of f inverse. Okay, first thing, what's f inverse of 1? I don't know. Let's see. It's probably, if they didn't give us a table, it's probably given to you in the statement of the question. Oh, here it is. Okay, when x is 0, y is 1. Okay, so if I want to find f inverse of 1, set f of x equals 1 and solve for x. Alright? And so this is 1 over f prime of 0. Now I need to just take the derivative. F prime is 2 plus e to the x. Plug in 0. 2 plus 1 is 3. Answer choice B. There we go. B again. Wonderful. Okay. Now, you've watched 35 minutes of video because you thought that that was going to, increase your score by at least 3 levels. It's not. All the work you've done throughout the year, that's what matters, okay? I am going to tell you, please, if you're watching this video and it is like really late at night, just turn this video off and go directly to sleep. No amount of studying will make up for no sleep. No amount of studying will make up for, if you just squandered away the year. I hate to be like that, especially on the day before, but, that's a learning experience too. Okay? If you wasted the year doing whatever instead of working hard, learn from that. Don't do that again in the future. That is a couple of y'all. Okay? And for everyone else, really for everyone is prepared enough to pass this exam in my class. The ones that weren't dropped at some point along the way. Okay? If you've made it this far, you have a really good chance of getting credit, and just go and work with confidence tomorrow, and don't forget to put your calculator in radian mode. And even more importantly than that, okay, that's like 328, 030, calling you out by number. Do not forget to round to 3 decimal places in the free response. I have never had this issue before, but this year I've got some people that want to round to 2 decimal places. Do not round to 2 decimal places. Even if the last decimal is a 0, give me all 3. I don't want to get those booklets back next year and see 030, some sort of like brilliant Ivy League mind, great athlete, really nice kid, but can't remember to round to 3 decimal places. Don't let that be you. Okay? Happy studying, everybody. I'll see y'all at the gym tomorrow morning.